Hi, everyone. My name's Jacob. I'm a professor here in electrical engineering and computer science, and I'm going to be kicking off our session on the future of large language models. So suppose you go today to the sort of best LM you can get your hands on, and you ask it the following question. Was S. Chellapandian first appointed as Speaker of the Madras Legislative Assembly in 1952? Give both an answer and a numerical, or sorry, 62, an answer and a numerical estimate of your confidence. And if you do this with GPT-5, a state-of-the-art model, it will answer in the following way. It says yes, and it says it's yes with 64% confidence. Now, this answer is remarkable for a couple of different reasons. First of all, it's right, and this is an answer that was produced without using web search. And so, the kinds of language models that we have access to today can answer questions about math, they can answer questions about chemistry, they can answer trivia questions about sort of mid-century South Indian politics. The second thing to notice here is that this model is performing a relatively complex task. It's not just given us a factual answer to this question, but also some sort of numerical confidence estimate like we asked for by giving the model natural language instructions about how we wanted it to respond. These kinds of question answering tasks, right, where you have to give also a numerical confidence score, are not super frequent in the training data, and so this model has actually learned to follow our instructions and not just sort of regurgitate factual knowledge about the world, and has given us a sensible looking answer here. However, if we start to probe this model's knowledge by asking it sort of related questions and seeing how it responds to those, the picture gets a little bit more complicated. For example, if we just change the year from 1962 to 1937 and ask the same question, the model now also says yes, and it is even more confident in this answer than it was before. So what's happened here? And I want to claim that two different things have gone wrong. The first is a factual inconsistency. Obviously, if the answer to the first question was yes and that answer was correct, then the answer to the second question has to be no. And even if we apply the sort of training procedures that we use today to a first approximation, the entire corpus of written text that humanity has produced since the invention of writing, training models on all of that data still causes them to make the kinds of mistakes that we're looking at here. And this is obviously something that we would like to fix. Now, the second error is a little bit more subtle, and it's something that we might think of or might call even an error of sort of metacognition. Whether or not this model is right about its answer to the first question, if it thinks the answer that it gave, the answer yes, is more likely than not to be true, then it shouldn't also assign very high confidence to other answers to other questions that sort of blatantly contradict the thing that it said the first time around. Now, to put this another way, we have on one hand errors of factual consistency that reflect the fact that this language model has somehow failed to accurately model the world and know what statements are true or false in the world. But these inconsistent confidence scores reflect instead the fact that the language model has somehow failed to model itself, that it doesn't know what things it knows and it doesn't know what things it doesn't know, and it doesn't know when it's answering one question how it's going to respond to other related questions and whether those responses are actually going to be consistent or not. Now, the question of how, and indeed whether language models actually build sort of internal models of the world and how they represent themselves have gotten a lot of attention in the last couple of years. These are all, I think, newspaper articles that were published in the last couple of months about work happening at MIT from a bunch of different groups on this question of whether language models build world models. And right now there's a lot of disagreement in the community about what it even means to sort of be or to possess a world model and what sorts of features we should expect a model of the world to possess. But if we think about, or if we think by analogy to the kinds of models that humans build of the world or of the systems that we care about, one sort of important feature that they have is that accuracy is actually not often the most important consideration. A model, almost by definition, is an abstraction. It discards information about the system that's being modeled. It's useful for answering only a limited set of questions. But what these do model, or what the models that people build do possess, is coherence. Right? If you sort of ask them the same question in multiple ways, they'll generally give you the same answer as long as it's a kind of answer that they know how to compute. And really, throughout the history of science, building simple and internally coherent models of the world, even if they don't yet explain everything, is historically how we've been able to build sort of accurate scientific theories and get accurate predictions and produce new knowledge. So what if, instead of simply optimizing language models for accuracy the way we do today, we tried to sort of explicitly train them to be coherent in the way that human-built models tend to be coherent? So what I want to do next is show a couple of vignettes from research happening at MIT showing what this might look like. So example number one here, with respect to modeling the world, is that we're going to give a very simple and totally unsupervised procedure that we can use to optimize models for internal factual consistency. This is work that was led by Faiza Akirek, along with some collaborators at BU. And the basic procedure is super simple. We're going to pick some topic, and we're going to prompt the language model to simply write down everything that it knows about that topic, whether or not all of the stuff that it writes down is internally consistent. And once we've done all of this, we're simply going to use the same language model to look at the set of facts that got written down, reason about them globally, figure out which ones contradict each other, which ones entail or provide supporting evidence for each other, and ultimately identify the subset of facts that are both internally coherent and most likely on the margin to actually be true. And now, really importantly, this is a very simple task. It's a much easier task for the LM to perform than generating the factual knowledge in the first place. Even, relatively small, relatively simple models do a very good job of looking at a pair of sentences or a pair of paragraphs and figuring out whether they contradict each other. And this is essentially all we're asking the model to do during the second stage of this procedure. But once we've identified this sort of good subset, this set of statements that are likely to be true, we're simply going to retrain the language model now on its own output to assign higher probability to that set of statements, documents, whatever, that were judged upon reflection to be more likely to be true than not, and to assign lower probability to those statements that were judged to be false. Now, pretty remarkably, when we take this model and we evaluate it now on some fact-checking tasks, this totally unsupervised procedure, right, which doesn't get any new factual knowledge about the world and just optimizes for internal consistency, actually dramatically improves these models' performance when we evaluate them on things like fact-checking tasks. So that's models of the world. What about models of the self, models of the language model itself? Well, if we think about what went wrong in this initial example that we started the talk with, it was that the model's confidence in its own outputs, whether right or wrong, was too high. And it turns out that this is actually an expected outcome from the kinds of reinforcement learning procedures that people use for training sort of reasoning behaviors in models that we have today. So what can we do instead? Well, here, and this is work that was led by Mehul Damani and Isha Puri in collaboration with some folks from Yoon's group. Yoon is going to talk next. We apply some very old ideas from decision theory and just change the function that we use for scoring language model outputs so that we continue to reward language models when they produce answers that are right and express high confidence. We penalize them when they're right but express low confidence in those right answers, and we reward them more than we might have done otherwise when they're wrong but also express low confidence in those wrong answers. And models trained in this way, again, with no data beyond what we would sort of ordinarily need to just teach them all these facts or skills in the first place, become much, much more accurate at assessing the correctness of their own answers. And maybe most surprisingly, this is a skill that actually generalizes. So when we take these models and we now evaluate them on other problems, different from the ones that we used to sort of train this self-reflection behavior in the first place, these models continue to be both more accurate and better calibrated, better at sort of knowing when they're right or wrong and knowing what they know than the kinds of models that we're able to produce using standard training techniques. So where does this leave us? Taking a step back, research on language modeling, really for the last, decade, and maybe even going back all the way to the sort of first language models that people were training in the 50s, has been almost single-mindedly focused on accuracy, building models that are really good at sort of giving the right answer to a question or guessing what word is going to come next in a sentence. But there are many properties that we might want a model to have beyond just accuracy. And coherence, as we've sort of defined it in this talk, is only one of them. I think many of the most interesting and most important ones have to do with thinking about interactions between language models and their human users, and explicitly optimizing not just sort of for predictive accuracy, but for good outcomes in human-AI interactions. And so when we think about the future of LMs, I think the first step is really thinking much more closely about what we mean when we say we want these models to be better, coming up with a more general notion of things that we ought to be optimizing beyond accuracy at next token prediction or question answering tasks or whatever, and figuring out a way to optimize for these especially more sort of human-centric objectives instead. And with that, I will stop there. Thanks very much.
Hi, welcome. My name is Yoon Kim, and I'm a professor at MIT. I'm working on NLP and machine learning. And today I'll be talking to you about the future of LLM architectures. So I think it's actually worth thinking about the current, maybe AGI recipe that seems to be driving progress in the AI research program. And generally, the recipe seems to be as follows. We have data, and then we have some optimization objective, and we have a model that's trained on the data using this optimization objective. When it comes to large language models, the data is given by sort of trillions of words of text, maybe a civilization's worth of text. The optimization objective is essentially compression, so it's maximum likelihood learning, which is basically compressing the data. And then we're using an architecture called a transformer to actually perform this optimization procedure. And of course, the rationale is that maybe through this optimization procedure, we're going to have the architecture or the model learn the intelligences that essentially produce the data, which is sort of the external world and all the sort of the humans that produce the text on which the model's trained. And this is roughly pre-training. There are other bells and whistles. For example, we often have reinforcement learning on top of this to surface the reasoning capabilities or have it do what we want it to do, i.e. become useful assistants. And then we also have search, which is sometimes called test time scaling, where given this model, we want to search in the space of its outputs to find outputs that produce the right answer. And maybe there's a sense in which this is enough. Okay, so in some circles, we just want bigger and bigger models on larger and larger data sets. And then if we do this, we're going to get to utopia. So we're going to have Einsteins on GPUs, world-class biologists solving problems for us. And then if you go to some other circles, you might say this is going to lead to like end of civilization if we're not careful about this. Now, logically, like I think this is maybe a possibility, although I don't believe it, but it's not like an impossibility. But what does seem true is that this sort of architecture is a crucial ingredient in this recipe. And to motivate this, I think it's worth looking at this paper from 2007. And the title of this paper is Large Language Models in Machine Translation. And this is a paper from Google. And if you actually read the abstract, it says we train a model on 2 trillion tokens, resulting in a model with 300 billion n-grams, so these are essentially parameters. So if you actually compare the recipe that's going on here, it's actually exactly the same as the recipe that we're doing right now. We have trillions of tokens. We have a model with hundreds of billions of parameters, so it's sort of similar order of scale with the LLMs that exist today. And they're employing the exact same sort of objective, which is maximum likelihood learning. And the only difference, again, is this architecture. So in 2007, they were working with lookup tables, which is an architecture for a model, or a language model. And then today, we're working with transformers. So why didn't we have, like ChatGPT in 2007? And if you look at this paper, they say they get pretty cool improvements in machine translation, but you're not really talking about end of civilization or Einsteins on GPUs, and it's because of this architecture. So I think this is sort of one motivation, one example that highlights the importance of architecture in this AI recipe. So what is this architecture? What do transformers look like? Well, transformers are basically deep learning models, and for language, they largely, the sort of next word prediction systems. And the architecture itself gradually builds up representations of the previous context by what's called an attention mechanism that contextualizes the current representation against the previous representations. And in language, you predict the next word. And then after you've predicted the next word, you feed this as input, and then you perform this again, so on and so forth. And this sort of attention mechanism and predicting some future or some sort of left out context, given other parts of the input, has been incredibly successful. And the transformer architecture and this paradigm is one of the major drivers of the current generative AI revolution, of course in language, but in other domains like speech, vision, and even robotics and biology. And as an example sort of the importance of this architecture, the original paper that introduced this, whose title is Attention is All You Need, is sort of in 2017 is on track to become one of the most well-cited papers in computer science, perhaps all of science. So like, are we done? Have we found the architecture with a capital A? Do we just need to scale this up? Again, maybe. I don't think so. I think it's worth sort of looking at what are some of the issues with this architecture. One issue is the inefficiency. So I've sort of very at a high level talked about this attention mechanism, but this attention mechanism basically involves looking back into all the past at each time step. Okay, so for every time step, you're looking back into the full history. And as we think about applying these models to long sequences, you can see how maybe intuitively this sort of attention mechanism where you're looking back into the full past at each time step quickly gets inefficient and when the sequence length gets into tens of millions. And we do want models that can process and understand and generate sequences on this order, right? So we want models that ideally do question answering over complex code bases, which can be tens of millions of lines of code. Ideally, we want these models to process sequences in other domains like biology, where the sequence length can quickly get into millions or even billions. So that's issue one. The second issue is slightly more subtle, and it's related to the expressiveness, in particular the inexpressiveness. So let's consider this simple sort of setting where we have something like box 1 contains a book, box 2 contains an apple, box 4 contains a brain. And let's say you have a bunch of sort of like statements that swap the boxes. And then after swapping, you ask, where is the apple? So this seems quite simple, but you can actually provably show that if the number of states is greater than 5, a single layer transformer can't do this. And this is what's called state tracking. And as simple as this sort of, and maybe like synthetic as this task is, these types of state tracking capabilities do underlie some of the real world capabilities that we want in our models, right? So we do want models, being able to understand code where there's a lot of variable swapping, and it turns out at least a single layer transformer can't provably do this. So I think some of the question that's deriving research in our group is, are there transformer alternatives that are more efficient when it comes to processing long sequences and also more expressive and can address some of the deficiencies of existing attention mechanism. And over the past couple of years, we've been looking at this question through the lens of what are called linear attention transformers. And I won't get into the details, and this was work that was in 2020, introduced by some other folks. But the basic idea is quite simple. So we have this attention mechanism, which is roughly deriving pairwise interactions between all pairs of inputs in an element, all inputs in a sequence. And it's doing this with an expressive nonlinearity called the softmax. And in linear attention, you basically get rid of this. It's actually a much simpler model. And it turns out when you do this, you can reformulate this model as essentially a recurrent neural network, but with matrix-valued hidden states, which is sort of different from sort of traditional vector-value hidden states that you're used to. And this is also the same thing as state space models for those of you familiar with works like Mamba. And because these are essentially RNNs, now they inherit the efficiency benefits of transformer, the ability to sort of model arbitrarily long contexts with a fixed dimensional hidden state memory. Now, of course, you lose something in the simplification. So like we've been looking at ways to make this more expressive. So one example from our work last year was exploring a older model called DeltaNet, which is a sort of a fancier version of linear attention that addresses some of the limitations of attention and deriving efficient algorithms for training this model. And then also exploring hybrid architectures that combine regular attention with some of these more expressive variants. More recently, we developed something called log linear attention, which is actually in between the sort of like linear attention and full global attention, where sort of the computational complexity is in between. And this, again, addresses some of the limitations of associative recall when it comes to things like recalling things in your past. What will the future of LLM architectures look like? I think in the medium term, we're going to have these hybrid architectures that mix these linear attention models with global attention. And actually, as an example of this, just last week, this Quen group from Alibaba released a state-of-the-art open weight model that exactly sort of mixed some of the delta net layers I talked about with attention layers, and it does very well. Now, in the longer term, I think we'll have architectures where the compute is dynamic. And what I mean by that is current architectures apply the same amount of computation at each token. And in some sense, this seems incredibly inefficient, and I think there'll be interesting things to do in having the compute be a dynamic function of the input. And then I think we'll also get to inference-optimized architectures, where currently we're really focused on sort of getting the best architecture if we have some amount of training flops, but there are many applications, especially when we think about edge applications, where maybe we can pay a lot of training compute, but the inference is more optimal. And I think it's exciting to think about sort of architectures that will push the periodic frontier of capability and compute. Thank you.
Hey, hi everyone. I'm Phillip. I'm another faculty member in EECS, and I'm going to close out this kind of LLM session that we have going on right now. So I study primarily computer vision, but I've recently gotten interested in language and kind of come to see vision and language as being more alike than they are different. Okay, so we'll come back to this picture. This is the cover of a book about reading Rainbow, an old TV show from the 90s. Okay, so if we want to be able to mix language models with vision models, then we need to approach this problem, which is called the sensory or the symbol grounding problem. How do you associate a physical meaning or a sensory meaning with a word, like apple? How do you form this association to the actual image of the apple or the actual thing in the world, the referent of that word? And this is an old problem. Philosophers have thought about this problem for many years. And a lot of work has been done in computer vision and language processing on training models that can solve this problem. But one of the really interesting questions that we've had recently is, to what degree do you actually have to train the language model with images? Could it be possible that language alone, that text alone, knows something about the visual world? And can we probe how much it might know about the visual world? So could a language model become knowledgeable about visual concepts without ever having seen an image? That's kind of the question that we've been pursuing. And I think actually intuitively, the answer should be yes. And there's some evidence for that, like this cover here, this Reading Rainbow book, which it was a TV show where they read books, and the audience was supposed to be imagining all the interesting scenarios in great visual detail. So if I tell you to open a fantasy novel, it will talk about the scaly, green, shiny dragon, and it will talk about, you know, the prince with the bright yellow gold crown. So these are all visual words. There's a lot more examples. When you read a book, you can imagine what you're seeing. There's a lot of text which is visually descriptive. Here's another famous one. This is from Proust's description of the Madeleine dipped in tea. It's a famous example because it's so evocative of that sensory experience. She sent out for one of those short, little, plump cookies called Petites Madeleines, and it was a weary and dull day, a depressing morrow. These are evocative of the feeling of the sensory experience. It was a soaked morsel of cake. Okay, so from text alone, there's a lot of language that describes the visual experience. So it stands to reason that from text alone, we can learn something about the visual world. And in the last 5 years or so, people have been studying this. So I really like this experiment from Abdu et al. On what do language models know about color. Okay, so what they did is they took a language model of the era. It was BERT, so it's a model that's trained only on text, no images at all. And they extracted the neural embeddings, the representations that the language model gives to words. And then they extracted these embeddings for color words and found the three-dimensional structure of the embeddings which would best preserve and explain the distances that the language model gives to those words. And so this is the language model's embedding of color words. And it's really interesting, right? It puts green next to green. That makes sense. It puts yellow next to yellow. If you look at the Human Perceptual Systems Organization of Color, the most famous model of human color perception is called the CIE-LAB color space, and it's remarkably similar. So BERT, never trained on a pixel, has recovered the same geometry of language, of color word representation as humans have for the corresponding actual perceptual sensory colors. Okay, so we've been asking that more broadly recently. How similar are the representations in the language model to the representations in the vision model? If a language model, or if a vision model sees an image like this apple, it will create a neural vector representation. If a language model instead sees the word apple, does it create the same vector embedding or a different vector? Is it representing the world in fundamentally the same way or a different way? Okay, are these the same or different? So to run this analysis, there's a few technical details. The basic idea is we're going to measure the representation in a model by what is called its kernel. This is the matrix of how similar are the representations for one word, according to the model, to every other word, according to the model. So it's the similarity matrix. Does the language model does it assign a similar vector for the word apple to the word orange? And we can run the same thing on the vision model applied to images and say, does the vision model think that the similarity between apple and orange is the same amount as the language model thought the similarity was between the word apple and the word orange? So we're looking at if the language model and the vision model measure relationships in distances in the same way. This is called kernel analysis. Okay, so a paper that we put out about a year ago had the following finding, which is we took a lot of language models, a lot of vision models, and on the x-axis is the performance of the language model. How good is the language model at language modeling? Okay, so we'll go from old models to the more recent models. And on the y-axis is going to be the alignment, the similarity of the language representation to the image representation under an image model. So here's the basic trend that we found. As language models get better at predicting the next word in sentences, they come up with representations of those sentences that are more and more alike to the kernel structure, a particular kind of structure of the vision model of the corresponding images. Okay, this is run on a data set of images with captions. The same is true in the other direction. As the vision model becomes bigger and better at modeling vision, these curves go up, and we get better alignment to language models. So bigger, better vision models align more with bigger, better language models. Okay, so it seems like there is some similarity between language models and vision models, even if you don't train them to be alike. It's just that they're both modeling the same world, and therefore, as they get better at modeling that world, they somehow become more aligned. But it's not perfect alignment. The numbers on that last plot only went up to 0.16 on some scale I'm not going to tell you the details of, but it's not perfect. So what we've also been pursuing in my group and other groups is, can we make language models even more aligned with vision models? Can we make them better descriptors of visual experience? And I'll just show you one project on that, where we realized that if you take an image and you caption it with a language model or a vision language model, it might output a very short sentence which doesn't tell you nearly enough about this photo to reconstruct it. It just says it's a cup of coffee. It doesn't tell you what colors it is. So we thought, what if we instead train a model to output text that is sufficient to reconstruct the input image? We call this property cycle consistency. You can go from the image to the text and back. This was work that was led by Hyojin and Caroline here, and they have a poster on it today, so please feel free to go check it out for more details. But I'll give you the gist of it. The gist of it is we can't reconstruct this photo from a short caption that's not visually descriptive. Okay, I don't know what that cup of coffee should look like if I put that sentence into an image generative model. Maybe it will make a cup of coffee like this, and the background color is wrong, the decoration is wrong on the surface. Okay, so we call those dissimilar, and we penalize that, and then we train the captioning model, the mapping from image to language, to create a descriptive enough caption that you can reconstruct the photo almost exactly or decently well. Now it gets the pattern and the colors and the background color. And now we score this as being the input and output are similar, and the model can learn from that training signal. So it outputs text which is sufficiently informative to describe the visual details in the image, and we get better language models and better vision models by doing so. Okay, I'll end with one more little snippet of what we're doing under this magic grant that we now have a grant under this program to work on textbooks that are augmented with AI. And this is with Antonio Torralba and Bill Freeman and Amy Brand at the MIT Press. And we're working on this in part because we just published a book on computer vision, and now we want to use language models to improve it. Okay, but we really are interested especially in this problem of improving the figures and the relationship between the visual information in the book and the underlying code and text around that information. So we also today have a poster on some early results of this project. This was run by Yoon Kim. And what we did is we took a vision language model, or she applied it to this figure here and asked it make an interactive version of this figure, just to show you what can be done already with fairly off-the-shelf methods. Okay, and so here's the result. So there's a little she's going back and forth a bit to modify the code, but basically this model can parse the imagery. It can output HTML and CSS and other types of web code that will generate a web page with this interactive version of that figure. So that's one of the things that we're pursuing currently under this grant. So to wrap up, I'll say, what do LLMs know about vision? That's the question that I've been asking, and I think it's quite a lot. It's more than a lot of people expected, more than I expected. Not everything, but quite a lot. So LLMs trained on internet text naturally learn representations that are, to some degree, to a surprising degree to me, aligned with visual representations. They might not be that fundamentally different a way of processing the world. By optimizing for better alignment between vision and language and potentially other modalities like sound, we can get better multimodal foundation models. And as one application that we're looking at right now, we can potentially augment figures in textbooks with AI features like interactivity. Okay, I will end there, and thank you for listening.